Hello everyone. In this video we are going to talk about some properties of context-free languages and the decision problems. So we will first start with pumping lemma. So pumping lemma for context-free grammars is, the purpose that we care about this lemma is that this is exactly something similar to what we discussed for regular languages. For the case of regular languages, we defined pumping lemma, some property that all regular languages have that property, and if a language doesn't have that property, we can say the language is not regular. So we care about the pumping lemma to show that some language is not, for example, regular language. Nicely, there is a similar property for the context-free languages that we will show that this property holds for all context-free languages, and if a language doesn't have that property, so we can prove that language is not context-free language. So what is this property is saying? Before actually give you the formal definition, I'm going to give you a couple of facts and observation about the grammars for context-free languages. Here we assume that the context-free grammar that we work on is in a form of a Chomsky normal form, CNF form. We have talked about this one previously, right? How to convert any context-free grammar to Chomsky normal form. And the form of, the Chomsky normal form was that every rule is going to be either in the form of A go to some terminal, or your variable goes to two other terminals. Okay? And we proved some theorem about the in the parse tree of any string generated by context-free grammar in the form of Chomsky normal form. We proved that for any string W, the length of the string will be less than or equal to 2 power the height of the parse tree minus 1. Which basically gives us some lower bound for the height of the parse tree. Basically, we assume that we have the string, we wanted to find some constraint over the height of the subtree. So it's actually telling me that if the length of the string is greater than 2 power m, then I can conclude that the height of the parse tree, it doesn't matter how you write the grammar or what is the language, the height of the parse tree definitely is going to be greater than or equal to m plus 1, which directly you can actually just conclude it from this theorem. Okay, so now all of these facts, I have written them here. Just assume that I have I have context-free grammar. This is in Chomsky normal form, and I have generated a string from this grammar. And assume that the strings that I am generating is going to have the length greater than 2 power m, where m is the number of variables in the grammar, in the Chomsky normal form grammar that I have written for the language. Okay, these parts are not they are not a fact. I'm just assuming. I'm assuming that I have a Chomsky normal form grammar, which I have m variables in that grammar. Okay, then let's just take any string generated by this grammar that the length of the string is greater than 2 power m. Okay, I have actually taken some string z. the length of the string is greater than 2 power m, where m is the number of variables. These are just the assumption. Now I'm going to extract a couple of facts about the parse tree that you can generate for this string. Okay, so assume this is the parse tree for the string z. Let me just clean up a little bit here. These are the facts that we wrote before. Okay, we have a context-free form, context-free grammar in the form of a Chomsky normal form with m variables. Then I just chose some string in the language generated by this grammar, which the length of that is greater than 2 power m. From this fact, I can conclude that the height is greater than or equal to m plus 1. This is exactly the fact that we, the theorem that we proved previously. Okay, so if this is the parse tree, I know the height of the parse tree is greater than m plus 1. What does this tell me? The height of the parse tree, if you think of it, is basically the length of a path starting from the root to a leaf node, where your leaf node is going to be, one of the symbols, one of the tokens in the string. Okay, but because this is Chomsky normal form, all the rules that you have are going to be in this form. Only the last rule is going to, only the last step is going to go to a terminal. Token. So all of the nodes in this path, all of these nodes are going to be variables. So how many variables I would have here? Because I know the height is going to be greater than m plus 1, I can conclude using the pigeonhole principle, I can conclude that in this path, there are going to be at least two nodes that have a label that the label is the same. They have the same variable label. Okay? So this is a fact. This is something, just the observation. If I took a string that the length of the string is greater than 2 power m plus 1, when m is all the number of variables in the grammar, I can prove that in the parse tree of this string, on the longest path, okay, this is the longest path among this green one is going to be the longest path. The longest path from the root to a leaf node, there will be, if you write down all of the variables here, or the label of all the nodes in along the path, at least two of them should be the same. Okay, the label of AI and AJ will be the same. So far, I have just actually go through the facts, and I just extracted a couple of facts here, some observation. The other thing that I can observe here is that I don't know what is the length of the height, right? I just know that this is going to be greater than m plus 1. So that repetition, I can also actually, get this observation, this fact that this repetition will happen in the last m plus 1 set of variables in this, on the path. The path can be m plus 1, can be greater than m plus 1. I don't know what is the length. the only thing that I care here is that in the last m plus 1, there is the last m plus 1 variable, there is a repetition. There are two nodes that have the same label. What does this, having two variables that have the same label tell me? It tells me actually a lot. It will help me to write down the pumping lemma property for me. Just before write down that, I'm going to actually show you something. The whole string Z can be divided to 5 different parts. Okay, some part of it will be generated by, this part of the tree. This is, let's actually just call it U, right? Before the variable, the variable that we found that will be repeated. And be careful, you might have more than, a couple of other actually variables can be repeated as well. I only care about those two variables that happened, and I can make sure that definitely there will be at least one repetition in the last m plus 1. So I'm just caring about this part. You can have more repetitions here. I don't care about them. Okay, so this part of the tree will generate some string. Let's just call it U. This part of the tree will generate some other part of the string. We will call it V. This part of the tree will generate some other part of the string. We will call it W. This part will generate some other part of the strings X. This part will generate some other part of the string Y. And the full string will be the concatenation of all these parts. U, then V, then W, then X, and then Y. Okay? So what we know about these parts? I don't know what is the length of U, what is the length of Y. I don't know what is exactly will be the length of V, W, and X separately. But I know something, that this part, V to X, has been generated under the subtree with the root AI, A sub I. And what is the height of this subtree? I know that the height of the subtree is m plus 1. Okay? So it tells me that there is a restriction over the length of this part of the string. So not only I know that if you actually divide the string to these 5 different parts, I can conclude a fact about the length of the middle part here from V to X. That I know that the length of this part is going to be smaller than or equal to 2 power the height of this subtree, the subtree that generates this, minus 1. The height of that subtree is m plus 1. So the length of W, V W X is going to be less than or equal to 2 power m. This is the fact that I can actually conclude. Okay? Not only that, I also know that because there will be just some repetition between this AI and AJ. I don't know where they have been actually repeated. They can be just directly after each other or completely separated from each other. But I know something that at least one a string will be generated either on this part or either on this part. So I can also conclude this fact that, okay, Vx the length of Vx, one of them should be at least non-empty. You cannot actually have both of these two as empty. And what is the reason? The reason is that we don't have any epsilon production, we don't have any unit production in our grammar. That is the reason. So definitely the length of Vx is going to be greater than 1, greater than or equal to 1. Okay? The reason is that we don't have unit production, we don't have epsilon production in the Chomsky normal form. Okay, so what this tells me in total, at the end, all of these facts, these are just actually facts that I have extracted. These facts helps me to find a repetition. This is something that I needed to define my pumping property, pumping lemma. Remember, in the regular languages, the pumping lemma was a property that you find some loop in the DFA and say that, okay, because there is a loop in your DFA, all those strings that are generated by going through that loop in your DFA, you can extend them by pumping the part of the string which actually labeled the cycle. You can pump that cycle and generate different type of strings, and all those strings should be a part of the language as well. We are looking for the same, for a repetition, that if we repeat something in the string, all those new strings after the repetition can be generated after the repetition. They are going to be a part of the language as well. Okay, so let me show you that repetition here. This is the original tree that we have, right? You have this string. The length of the string is greater than 2 power m, where m is the number of variables in your Chomsky m is the number of variables in your Chomsky normal form grammar, and we found a repetition. Okay, a repetition in the variables of this path. So because these two variables are the same, it actually tells me something. I can instead of this one, I can just put this subtree, right? So the resulting subtree would look like this. This is actually too big, but let me draw something smaller. So instead of here, this node AI, I can put the whole subtree of AJ. AI and AJ are the same actually, right? But by replacing AJ here, it is just like I have removed this part and this part. What will remain is that here you have W. Here is the part that is generated by U, and here is the part that is generated by Y. So if Z is a part of the language, also a string like UWY is also a part of your language. If UVWXY is a part of the language, you can conclude that this is a part of the language as well. Not only that, I wanted to actually tell you that if instead of now this time, if I replace AI here, it's just like the subtree of AI that you have. If you just take it and put it instead of AJ once, you would get a tree like this. That here you have AI, okay? Take the whole subtree and repeat it here. Again, put the AI here. What you get under AI, again, AJ will be here, right? what are these labels? So I know that this is going to be U, just like before. This is going to be Y. This was W, right? This part, this AI, is exactly whatever you have here. I've just repeated it here. So V, X, and you have from one V and one X from before. So you also, if this is a part of the language, so also you can say that U, V, V, W, X, X, Y is also a part of the language. You can actually just see that I have repeated AI once. So it basically actually gives me this idea that if I repeated it for K times, all the strings in this form are going to be a part of the language as well. Where what is K can be 0, K can be 1, K can be 2. When K is 1, this is going to be this one. When K is 0, this is going to be this language. When K is 2, this is going to be this language. For all the values of K greater than or equal to 0, this strings in the form, this form is going to be a part of the language. So we found some repetition in the parse tree and just show you that, okay, by pumping this repetition, this loop, you are going to generate more and more strings that all of them will be in the language because all of them can be created by the corresponding grammar. Here it actually just shows you the full part of it, that if you repeat K, if you repeat AI more and more and more for K times, all of the strings in this form are going to be a part of the language. If K is 0, this is going to be this case. It's just like you remove the outer subtree. So now we can write the pumping lemma formally. That we will say that here again there will be some constant for our pumping lemma for the context-free languages. We will call it n, where for the regular languages n was equal to the number of states for the DFA that you design for the language. Here n is going to be a number, for example, equal to 2 power m, where m is the number of variables in your in the context-free grammar that you write for L. So if L is a context-free language, it means that there is a grammar, context-free grammar for that. So just assume that n is 2 power m or anything greater than that. For all the strings in the language, if the length of the string is greater than n, remember we put this assumption here that the length of the string should be greater than 2 power m. Otherwise, you cannot make sure that you have repetition in the tree. You cannot have actually this repeated form of the subtree. So this is the part of the assumption. The length of the string should be greater than n, should be greater than this 2 power m. Then for any way that you divide z to 5 parts, where we have actually this constraint over these 5 parts, that the 3 inner parts are going to be, the length of them should be less than or equal to 2 power m, okay? And the Vx cannot be empty. Vx should at least have one symbol. For any value of k, if you pump Vx, so it just tells you that it doesn't matter how you divide it. No, it tells you that actually for the way that you divide it, there should be some way that if you divide it for any time that you pump V and X, all the generated strings are going to be in the language. Why it is telling you that there exists? Because it actually just tells you that, yeah, there will be some repetition in the parse tree. Find it for that part. If you repeat, if you pump, all the generated strings from the new trees that you create will be a part of the language. So how we are going to use it to prove a language is not context-free? This is exactly similar to the way that we played with the pumping lemma for the regular languages. We have to use the theorem in contrapositive way. And the reason is that there are some languages that the pumping lemma for context-free languages holds for them, but they are not context-free. So this is not if and only if statement. You have to actually use it in a contrapositive way. It means that if this part doesn't hold, you then negate of the second part. If it doesn't hold, you can prove that the language is not context-free. So we are going to just use it exactly similar to the way that we did it for the regular languages. We assume that someone would claim a language is a context-free language. Then you have to choose a good string that it doesn't matter how you divide it to 5 parts. You can always show that there will be some k that if you pump the vx part for k time, the resulting string is not in the language. So in this case, we will win and we will show that the language is not context-free. So let me show it to you over an example. Remember, this was the very first example that we saw. It was not context-free language, and we are going to show it using the pumping lemma. So we have this language. We wanted to show that the pumping lemma doesn't hold for this. So we assume at first that this is context-free. If it is context-free, you can write a grammar, context-free grammar for that in a form of a Chomsky normal form with m variables. Okay, so m is going to give me that constant, right? So take a string with length greater than 2 power m. Okay, so what string I can actually choose? Let's just take a string z equal to a powers n 1 power n, 0 power n, 1 power n, and 0 power n, where n is equal to 2 power m. It was hard to actually write it in that way, so I'm just writing it using n. So the number of zeros, ones, and zeros here are going to be equal to 2 power m. Okay, so now this is the choice of the opponent. The opponent can divide the string to 5 parts, but under these constraints, that the length of the 3 inner parts are going to be less than n. Okay, and I don't care about the length of the u or v, the u and y, but the length of vx should be greater than 1 as well. Okay, so I have now proof that it doesn't matter how the opponent can actually, it doesn't matter which division, which way the opponent is going to split, always it is possible to find some k that show that if we pump the string, the result is not going to be in the language. So what are different possibilities to divide the strings to 5 parts? If you have a string like this and you have these constraints, you can divide it either in 5 different actually possibilities. That the first possibility is that the UVX part is totally covered in this part, or either totally covered in the one part or totally covered in the last part here. These are 3 different cases. The other 2 cases is that the so in all of these cases, I'm saying that VWX is either here or here or here. There are two other cases that VWX can be a set of 0 and 1s here, or it can be a set of 0 and 1s here. So in total, there will be 5 different possible cases for VWX. Either totally in the 0 part, or totally in the 1 part, or totally in the last 0 part, or on the boundary of 0, 1 part, or on the boundary of 1, 0 part. And it is not possible to have it over the 0, 1, 0 part. Why? Because the length should be less than 2 power m. Okay? Because of this constraint, we only have these 5 different possibilities. So for each of these cases, we can prove that if you pump it for any number of times, the result is not going to be in the language. So let me actually show it to you for a couple of cases. If it is all in the first 0 part, what does this tell you? It tells you that if you pump it for example, 0 times, the result is going to look like you have in this case, let's just assume that in this case, Vx, both of them will be a couple of zeros, right? Let's just assume that Vx will be some 0 like R number of zeros, right? So in that case, Uwy, if k equal to 0, this is going to look like 0 power n minus r, 1 power n, 0 power n. And we can see that this is not a part of the language, right? Because the number of zeros here is not equal to the number of 1 and zeros. Similar to that, you can actually prove this part. You can also prove this part. For the boundary cases, for example, for this case, we can assume that, okay, V is going to be some zeros, X is going to be some 1, or, completely vice versa, doesn't matter. So V and X, so the part Vx can be a couple of zeros, a couple of 1s, just zeros, just 1s, or some 0, some 1. It doesn't matter how many actually 0 and 1s you are using here. Let's just use a different name. 1 is at the end, if you remove Vx, the number of zeros and 1s in the result is not going to be equal. So either actually some of these zeros or some of these 1s will be removed, and they are not going to be equal in the resulting string, and it's not going to be in the language. I know that writing down the full pumping lemma here is going to take definitely more time than when you are writing it for the regular languages. You should consider all different possibilities, but you get the idea that how the pumping lemma here actually works, right? And that's enough. We wanted to actually know that when we see a language, we can prove that if it is not a context-free language, using a pumping lemma, we can prove it. Another example, if you have a language like this one, WX All the strings are going to be just a repetition of some other, some binary string. This was not context-free language. So we wanted to actually prove that this is not a context-free language. Again, here we would assume there is some constant n, where n is the 2 power m. This is our pumping lemma constant. We will choose a string with length greater than m. This is our choice. So for example, just assume we have chosen a string like this one. This is a valid string in the language, right? And the length of it is greater than n, or constant, pumping lemma constant. So now we should prove that it doesn't matter how you divide this to 5 different parts under this condition that the length of VWX is less than n. If you pump the string, the result is not going to be in the language. And again, here you have a couple of different cases. VWX is all in the first part, all in the 1 parts, all in the 0 parts, all in the 1 parts. Not only that, you have to actually should consider all the boundary cases, that VWX can be in this boundary, it can be actually on this boundary, it can be on this boundary, right? But it cannot be actually covering more than these cases. So 7 possibilities. For each one, we can prove that if you pump the Vx part 0 or more than 1 times, it doesn't matter which one, you can actually always just generate a string which is not a part of the language. So this is not a context-free language. Just take this one again as your exercise. I mean, this is going to be something very similar to the other part. I mean, the other examples that I showed you. So I'm going to end this lecture with some closure properties and some decision property about context-free languages. So far in the previous lectures, we have seen that context-free languages are not closed on their, unlike the regular languages, they are not closed on their intersection, difference, and completion. If context-free language, if any set of languages, you wanted to prove that it is not closed under some specific operator, you can just prove it using some counterexample. And we already proved this. I mean, we have seen some examples for all of these cases. If you proved one of them, if you find some counterexample for any of these 3, because they are completely related to each other, you can, using the set theory rules, you can just prove that for the others it is context-free languages, they are not closed as well. We have also seen that the context-free languages are closed under union, because if you find a grammar for 2 languages, context-free grammars for 2 languages, you can concatenate them. You can actually just get the union out of the both grammar, add one more rule, and create a grammar for the union of the language. Also, we have proved it for the concatenation during the previous lectures. Killing closure, I will actually just keep it as an exercise for you, probably in your assignments. Context-free languages are closed under homomorphism and inverse homomorphism and substitution, which is a specific operator. I'm going to show it to you, and under reversal. So I'm going to show these 2 parts. Homomorphism is a simpler form of a substitution, so if I showed you that one, you can just prove the homomorphism and inverse homomorphism as well. So what is the substitution operator? We define the substitution operator S over a set of tokens in an alphabet as a language. So the substitution itself is a language, okay? So for any string in any given language, if you apply this operator, it is just like you are applying that substitution operator over every single token of the string W. Okay, so let me show it to you over an example. And one thing about this substitution, when I'm saying that substitution operator is itself a language, it can use a different alphabet, so be careful about that. So just assume that I have defined this alphabet, and I have defined the substitution operator S to be like this, that if you apply it over 0, it will replace 0 with a language. So be careful, this is not like a homomorphism. This is more complicated than homomorphism. You can replace, wherever you see 0, you can replace it with any string from this language. Wherever you see 1, you can replace it with any string from this language. This part is simple. It actually just tells you that I have 2 strings in the language, but this part is more complicated. This language is itself too complicated that it can actually have, it means that 0 can be replaced with AB, it can be replaced with AA, BB, it can be replaced with AAA, BB, B, or basically A power n, B power n for any value of n greater than or equal to 1. So if I have a string like W, 0, 1, if you apply the substitution operator over this string, the result is going to be the concatenation of applying the substitution operator over 0 and over 1, both 2 symbols in the string, which result in a set of strings, not just one. You can actually get this string, you can get this string. You can see that I replaced S0 with AB and replace 0 with AB, replace 1 with AA, replace 0 with AB, replace 1 with BB. So, and all of these strings are going to be in SW. Basically, SW is itself a set of strings. Itself is going to be a language. So no, the fact is, the theorem is, context-free languages are closed under the substitution operator, which means that if you have a context-free language and if you have a substitution operator, which itself is a context-free language, or all of the tokens that you define in the substitution, all of them are context-free language. If you apply all of these rules over a context-free language, the result is going to be a context-free language. So how can we prove this? So basically, when you apply that operator over L, it's just like you apply the operator over all the strings of the language, right? So if you have this language, this is going to be the set of all these languages itself is going to be the result. How we can prove this? The proof is very simple. You can actually just say that, okay, you have a context-free grammar for the original language. Use that to create a parse tree for every string in the language. So all the leaf nodes in the parse tree is going to be a terminal symbol, right? For each of those terminal symbols, we are going to apply the substitution operator. The substitution operator itself is a context-free language. So it is going to be a context-free grammar for each one. You can create a parse tree using the grammar of the other for each of those substitution operators, and it generates a parse tree that gives you the string for the S of W when you apply the substitution operator over the original W. Okay, so basically it's going to be the combination of all the rules in the original context-free grammar, and for each of the terminals you will add one more rule that goes to the starting point of a context-free grammar for the substitution operators. So let me show you an example of this. Assume that you have a language L, which is a context-free grammar. This is a rule for that. And I have a substitution operator for that for S, it gives you, this is the grammar. This is actually the previous example that I showed you, that for S0, the language is this. This is a context-free language, so I can write a context-free grammar like this for that. And this is a context-free language as well. Basically, because this is limited, this is a regular language. So it is a context-free language as well. You can write a context-free grammar for that, as simple as this. Okay, so I can just combine all of these in the original grammar, replace all of the terminal tokens with the starting point of corresponding substitution grammar, substitution operator. So 0 will replace with S0 and 1 will replace with S1. So the combination of all of these are going to be the final grammar. So the other operator that I wanted to show you was that reversal, which is actually very nice. That if you have a context-free language, it is if you reverse the language, when you reverse the language, you reverse all the strings inside the language. The reverse language is going to be a context-free language as well. How we can show that how we can prove that? Basically, the proof again is a constructive proof. What we can do is for every rule in the context-free grammar of the original language, you can, for all the rules on the right-hand side of the rule, just reverse that. Whatever it is, just reverse it. This is going to be the resulting a context-free grammar which generates the reverse of the original language, which is, I think this is very nice and neat. Here I'm going to actually show you a couple of other theorems and properties about the context-free languages and regular languages. Assume I have these three languages. What do you know about each of them? We know that L1 is context-free, right? We can write a context-free language for that, a context-free grammar for that. L2 is regular. How about L3? All binary strings that the number of zeros and ones are equal. We actually saw a push-down automata for this one before. So yes, this is a context-free language as well. So L1 and L2, L1 and L3 are context-free language. L2 is regular. And one thing that we know about all of these languages is that the intersection of L2 and L3 is equal to L1. Right? If you take the intersection between the strings that has equal number of 0 and 1s and this regular expression, you will get all the strings in this form, that n number of zeros followed by n number of 1s. So that is actually something nice that basically gives me a rule about context-free languages and regular languages. Context-free languages are closed on their intersection with regular languages. Okay, so basically I can say that I can prove that if for any context-free language and any regular language, if you take the union, the result is going to be context-free language. Although context-free languages are not closed on their intersection in general, but they are closed on their intersection with regular languages. Okay? So not only that, how about this rule? Can I say something about the set difference? CFL minus RL, a context-free language minus a regular language. Can I say something about this? Yes, I can actually conclude that this is also context-free language. The reason is that whatever is the regular language that you write here, you can calculate, you know that regular languages are closed on their completion, so you can write it as CFL intersection with whatever that language, the completion of that language. So this is going to be a regular language as well. They are closed on their intersection with context-free languages, so yes, the result is going to be context-free. But you cannot actually conclude anything about the union. About the union you can also conclude because the context-free languages are closed under the union. So if you take a union between a context-free language and a regular language, definitely this is going to be a context-free language. But you cannot actually conclude that it is going to be a regular language. You can just say that it is a regular context-free language. Okay, and I'm going to finish this lecture by just talking about the decision properties over context-free languages. Unlike regular languages that we could we could answer the decision problem we could answer many decision problems for regular languages. We cannot answer most of them for the context-free languages. The only decision problems that we can solve for context-free languages is the emptiness. So given a context-free grammar, does it generate anything or not? Does it generate a language which is empty or no? We can actually check that. How we can check that? You can just apply the simplification rules, removing the those variables which are not generating, then remove those variables which are not reachable. If you still have some variable in your grammar, so you can say that yes, your grammar generates a non-empty language. Otherwise, you will end up with an empty grammar, so your grammar generates an empty language. The other decision problem that we can solve is membership test. That given context-free grammar and a string, can we check that if this string belongs to the context-free grammar? Yes, we can do that. We can create a push-down automata for the grammar, and we can check if the string is accepted by that push-down automata or not. And basically the idea of this membership test is what the parsing algorithms do. The whole task of a parsing algorithm for a context-free language is that you give it the context-free grammar, then for any given string, the parsing algorithm just tells you that the string belongs to the grammar or not. Not only it checks the string belongs to that, it also generates the parse tree, derivation tree for you. This is exactly something any compiler do. All of the programming languages that we have is a form of a context-free language. I should say that there are context-sensitive languages. Anyways, I don't want to actually go through those details, but the task of a compiler is to find the parse tree. You give it a program, it tells you that if this program under this grammar is a valid a string generated by the grammar, by the rules of your programming language. But none of these decision problems are solvable. They are not. They are undecidable. We cannot solve them. If you have a context-free grammar, we don't have a algorithm that check a context-free grammar and tell you that this is ambiguous or not. So you have to do it one by one. For any given example, you have to check it yourself. We don't have an algorithm to tell us that. Or we cannot check that if a context-free language is inherently ambiguous. We cannot check if the intersection of two context-free languages is empty or not. We cannot check if two context-free languages, if you given two context-free grammars, if they are generating the same language or not. We cannot check if context-free grammar will generate the set of all strings over the alphabet or not. So, yeah, all of these problems are undecidable. And it actually just tells you that the context-free languages are way more complicated than the the regular languages, that we could answer all of these problems, these decision problems for them. So this is going to cover chapter 7 of your textbook. There are some good examples about the pumping lemma, the full proof of all the theorems available in your textbook. So please read the textbook, do the exercises, and if you have any question, we discuss it during the office hours.